Hello everyone, myself Heli Mehta, working as an assistant professor in Computer Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Our subject is Computer Network. Our unit is 4, that is Network Layer. So, a Unicast routing protocol. Routing table can be static or dynamic. Okay, so router is making routing table and it can be static or dynamic. Okay, so manual entries are done in a static table. Okay, dynamic table is updated automatically when there is a change somewhere in the internet. Okay, so routing table may be static or dynamic. In static, manual entries are done. Okay, and in dynamic it is updated automatically when there is a change in the internet. Nowadays dynamic table is used because of sudden change in the internet. Okay, one of the routers in the internet may fail or link between any two routers in down. So because of this reason dynamic table is required. So nowadays dynamic table is used and it is updated automatically. Routing protocol is a combination of rules and procedures that let routers in the internet inform each other of changes. So routing protocol is a combination of rules and procedures. See here, intra and inter domain routing. Okay, and internet can be so large, okay, that one routing protocol cannot handle the task of updating the routing table of all routers. So we have a multiple routers and all routers have a routing tables. Okay, so because of a large internet, only one routing protocol cannot handle the task. For this reason an internet is divided into autonomous system. Okay, so that is the concept of autonomous system. An autonomous system is a group of networks and routers under the authority of single administrator. Okay, so see in the diagram we have a multiple autonomous system. Okay, but the administrator is single. Okay, so autonomous system is a group of network. Here we have a one network, here we have another network, here we have another network, and here we have another network, that all networks are connected with each other. Okay, and they have a single administrator. That is a autonomous system. So autonomous system is a group of network and routers. Okay, routing inside an autonomous system is referred to as a intra-domain routing. So this is the autonomous system. So routing between this autonomous system is known as a intra-domain routing, and routing between autonomous system is referred to as a inter-domain routing. So if we have this autonomous system and this autonomous system, if routing is performed between these two autonomous systems, then it is known as a inter-domain routing. Okay. Now, several intra-domain and inter-domain routing protocols are in use. So remember this, intra means within one, inside the autonomous system. Okay, within one autonomous system, and between two autonomous system when routing is performed, it is inter-domain. So please remember intra-domain and inter-domain very well. Okay, so we have a several intra-domain and inter-domain routing protocols. Okay, so two intra-domain routing protocols are distance vector and link state. Okay, and one inter-domain routing protocol is path vector. Okay, so routing protocols are routing information protocol, that is RIP, is an implementation of the distance vector protocol. Okay, so for distance vector we have a RIP. Open shortest path first, OSPF, is an implementation of the link state protocols. Okay, so for link state we have a OSPF, and border gateway protocol BGP is an implementation of the path vector protocol. So remember this routing protocol. For distance vector we have a RIP, for link state we have a OSPF, and for path vector we have a BGP. Okay, so two intra-domain and one inter-domain routing protocols are there. We will see one by one. Okay, so this is the diagram. So routing protocols are of two types, inter-domain and intra-domain. Here I explain the concept of inter-domain and intra-domain. Okay, so inter-domain is path vector, and in path vector we have a BGP. Intra-domain means distance vector, and second is link state. So for for distance vector we have a RIP, and for link state we have a OSPF. So this is the classification of routing protocol. This is the most important topic. Okay, so first we will see distance vector. Okay, and then we will see in next lecture we will see RIP. Okay, so in today's lecture we will cover distance vector. So what is distance vector routing? In distance vector routing, the least cost, okay, so cost is low, least cost route between any two node is the route with minimum distance. So see in the diagram we have a multiple nodes. Okay, so one node is a source and one node may be destination. So from that source to destination we have a multiple paths. Okay, so we will distance vector routing select the least cost route. Okay, the least cost route is selected between two nodes and that is of minimum distance. Okay, in this protocol, as the name implies, each node maintain a vector means table of minimum distance to every node. Okay, so the table at each node also guides the packets to the desired nodes by showing the next stop in the route. Okay, next hopping routing. So see here we have a node A, B, C, D and E. So at node A we have a A's table. Okay, so see here from A to A we have a 0. Now A is our here we have a. So from A to B we have a 5. So from A to B and distance is 5. Now from A to C we have a 2 distance. Okay, so from here we are considering table for A, so we are calculating the distance from A only. Okay, so A to C we have a distance 2. Now A to D. Okay, so from A to D we have a 3. So A to D we have a 3. Okay, now E. For E we have a no direct connection. Okay, for E we have a 2 option. Okay, A to C or C to E. Okay, so this distance is 6, 2 plus 4. Okay, or we can select we have another path, that is A to B and B to E. So 5 plus 3 it is 8. So we select this 2 and 4, 2 plus 4 6. So E from A to E we have a distance 6 via C. So we are writing C over here. So from A to E we have to go via C. Okay, so A to C, C to E. So 2 plus 4 6. So distance 6 is, but we have to write over C. So like this, at node at each and every node we have a vector tables. Okay, so we will see B. Okay, so for here A B C D, but we are considering from A. So B to B distance is 0. Okay, from this node to node we have to write 0. Now B to A. So B to A we have a 5. So here at A we have a 5. Now B to C we have a 4. So at 4. Now we have to reach at D. So for D we have a 2 option this. From B to A and A to D, that is 8, 5 plus 3, or we can say B to C 4, C to A 2 and A to D 3, that is 9. 4 plus 2 plus 3. Okay, that is 9, and B to A and A to D, that is 5 plus 3 8. So minimum is 8. So here we have to 8. So we are going B to D via A. So we are writing A. So B to A and A to D. So we have to travel from A. So we have to write over A, write here A. Now B to E is 3. Okay, so this is the B's vector. Okay, now at D. Now for A to now we are considered from D. Okay, so D to A is 3. So we have to write over 3. To B we have to travel through A. So D to A to B. So distance is 8 and we are going through A. Now for C, D to A and A to C. Okay, then we can reach at 3. So 3 plus 2 5. So 5, and here we have to write A. Okay, D to D 0. Okay, now E. Okay, for E we have a D to A 3, A to C 2 and C to E 4. So 4 plus 2 plus 3 it is 9 on, and from D to E we are traveling through A. So we have to write A over here. So like this we have a C's table and E's table. So this is the vectors tables of minimum distance to every node. Okay, so this is the concept. Now the table for node A shows how we can reach any node from this node. Okay, so this table shows for table A from A to B, A to C, A to D and A to D how we can reach. It shows in the table. Okay, for example our least cost to reach node E is this. The route passes through C, that I have explained. Okay, if I want to reach at E, minimum distance is A to C, C to A. So we are not selecting A to B, B to E because distance is more. Okay, so we are selecting least distance. Okay, so this is the distance vector routing. Okay, now initialization. The table in the figure are stable. Okay, each node knows how to reach any other nodes and the cost. Okay, so here A, B, C, D, E, every node knows with distance how to reach to another nodes. Okay, So at the beginning, however, this is not the case. Each node can know only the distance between itself and its immediate neighbors. Okay, those directly connected to it. Neighbor means directly connected. So A's neighbor is B, A's neighbor is C, also A's neighbor is D. Okay, but we cannot say that A's neighbor is E, because A and E are connected via C, through C. Okay, so neighbor means directly connection. Okay, so for the moment we assume that each node can send a message to that immediate neighbor and find the distance between itself and these neighbors. Okay, the distance for any entry that is not a neighbor is marked as a infinite. So initially this is not happen. Okay, so the whole idea of distance vector routing is the sharing of information between neighbors. Okay, so although node A does not know about node E, node C does. Okay, so here A is not neighbor of E, so A have no information of E, but C have. Okay, C and E are neighbors. Okay, so the concept is, so if C shares its routing table with A can also know how to reach node E. Okay, so see here, A have no information about E because they are not neighbors. Okay, but C is a neighbor of E. Okay, so C have a information of E. Now what happens if C is a neighbor of A? Now C pass this information to A, then A can know how to reach to E. Okay, that is the concept. So on the other hand, node C does not know how to reach node D, but node A does. If the node A shared its routing table with node C, then node C also know how to reach D. In other words, node A and C as immediate neighbor can improve their routing table if they can help each other. Okay, so same concept. C is not a neighbor of D, so C have no information about D, but D is a neighbor of A. Okay, so A have a information of D. Now if A pass the information to C, then C came about how to reach to D. Okay, so this is the concept. So okay, initially what happened, so initialization of table in distance vector routing. So what happens, so we are starting from A, so A to A 0. Okay, now A to B direct neighbor, so 5. Okay, A to C they are neighbor, so 2. Okay, now A to D they are also neighbor, direct connection, so 3. Now A to E is not a neighbor of A. Okay, we can travel through C, they are not neighbor. Okay, so they have no direct connection, so here we have to mention infinite. Okay, we have to write the distance of only neighbors. Two nodes have a direct connection, then we have to write the distance over here. Okay, now for B to B 0, B to A 5, B to C 4, B to C 4. Okay, now B to D we have no direct connection, so we have to write infinite over here. Now B to E we have a direct connection, that is 3. So this is B's table initially. Okay, now for D to A direct connection 3, D to B we have a no direct connection, we have to travel through A. Okay, so we have to infinite. Again D to C we have no direct connection, so infinite. D to D 0. Again we have a D to E, no direct connection, we have to travel through multiple nodes, that is D to A to B or D to A, A to C and C to E, then we can reach at E. So we have to mention infinite over here. So at initialization what we have to do, if we have a direct neighbors, then we have to write the distance, otherwise we have to write the infinite. Okay, now updating, now we are updating the table. Okay, when a node receives a 2 columns table from a neighbor, it needs to update the routing table. Update takes 3 steps. So the receiving node need to add the cost between itself and the sending node to each value in the second column. Okay, the logic is clear. If node C claims that if distance to a destination is X and the distance between A and C is Y, then the distance between A and that destination via C is X plus Y. Okay, that I have explained. The receiving node needs to add the name of the sending node to each row as the third column if the receiving node use information from any row. Okay, the sending node is the next node in the root. The receiving node needs to compare each row of its old table with the corresponding row of the modified version of the received table. Okay, so if the Next node entry is different. The receiving node choose the row with the smallest cost. If there is a tie, the old one is kept. Okay. If the next node entry is same, the receiving node choose the new row. Okay. For example, suppose node C has a previously advertised a route to node X with a distance 3. Okay. So this I will explain in the example. So here we have a receive from A. Okay. So we have to calculate the distance from C. Okay. So C2 C0. Okay, so in this diagram we have to mention that. So C2 C0. Now C2A is 2. Okay, so in this table we have a 2 over here. Okay, now C2B is 4. Okay, so in this table we have a 4 over here. C2 C0. Now C2D we have a no direct connection. Okay, so C2D we have a no direct connection, so we have to write infinite. Okay, now C2E we have a 4, so we have to write 4 over here. So this table, okay, we have a receive from C, or we are consider this for from C. Okay, now A's modification table, as I have explained, here we have a x plus y. Okay, so from C2A we have a 2, so 2 plus 2, so that is 4 over here. Now for B it is 6 from C. Okay, so for A we are traveling from C. Okay, we are considering C, we are not directly going from here. So A to C and C to B, so we have a 4 plus 2 6. Okay, so here we have a 6. Okay, now C2A we are considered from C to A, so C to A is 2, so we have to write over here 2. Now from C we have a no direct connection. Okay, so for D we have to write infinite. Okay, C to D we have no direct connection, so we write infinite. Now for E we have a from A we have a 2 A to C and C to A, so 2 plus 4 6. Okay, so we have to write 6 over here. So this table is modified. Okay, now compare with old table that I have explained here, that is my old table. Okay, here we are writing infinite because we have no direction from A to E, so we are writing infinite. Now C is sharing their table with A, so A came to know how to reach at A, so we get 6 over here, that is E have a 6. So A is identified that we can travel to E via C. Okay, so if we have to travel A to E, we are using C, so our distance A to C, C to E, so 2 plus 4 6, and in third column we have to write the node, that is C. So here we have a to E we have a 6 via 6. Okay, now compare with old table. Okay, after comparing the minimum distances we are taking. Okay, so here we are comparing A to 4. If we are using this concept, then we have a 4, but this is 0. A to A 0, so we have to consider 0. Okay, now if we are going via C here. Okay, for B we have a 2 option, that is directly A to B, that is 5, and from directly A to C and C to B, that is 2 plus 4 6. Okay, so in comparison we have a minimum distance 5, so we are taking 5. It is not necessary that direct connection have a minimum distance. Suppose it is happened, then here we have a distance 10, and here we have a to C and C to 4, so this is 2 plus 4 6, so we consider this part. But here we have a 5 and here we have a 2 plus 4, that is 6, so minimum is A to B 5, so we are considered 5. Okay, now for C we have a 2, so we are remaining 2. Okay, for D we have a here infinite, and here we have 3, so we are considered 3 direct distance. Okay, for E we have a 6 and infinite, so we are having 6. So this is the concept. So A to A, final answer, A to A is 0, A to B is 5. Okay, so A to B is 5, A to C is 2, so A to C is 2, and A to D is 3, and A to E via C, that is 6. Okay, so A to D 3 and A to E, that is 6 via C. So that is the A's final table that I have explained at earlier. Okay, that is the final answer, but for that we have to follow these all steps. Okay, that this is the distance vector routing. Thank you.